Hello, Chemistry 19.4. Number 1 today is about half-life. Number 2 is Geiger counters. Number 3 is Curie. Number 4 is Becquerel. In terms of explaining those, while we look forward, when you go to do 19.5's read, there's going to be 4 new points from 4 different obvious categories that they'll talk about. If you just know the names of the categories, you'll be fine. A lot of the early stuff today gets cut off because, as I've said, the vocabulary can't last long in this chapter because it builds pretty fast. So today's stuff from 5 through 21 are gone. We'll keep the things from 22 down. Difference being today's 33 to 37 had 5 shorthand ways to represent 5 things. The next one will have 7, because since we ditched the alpha and beta particle question, the alpha and beta particles will jump in on that, so that'll go from 5 to 7. Explaining today's and previewing how it'll go, number 1's question will be, what is the half-life of an element? A half-life is just the time it takes for half of a radioactive mass to decay. It doesn't mean it disappears, it just turns into other things. So if my chalk had a half-life of 7 minutes, if you would come back 7 minutes from now, this would look like this. And if you came back 7 minutes after that, it would no longer look like this. It would look like this. And if you came back 7 more minutes after it looked like this, it would be half of that. And then every 7 minutes it would cut in half if it had a half-life of 7 minutes. And they talked about how some things have half-lives that are billions of years, some are seconds. But the half-life is how long it takes for something to decay in half. Not that it disappears, but half of it's gone and half of it turns into other things. Let's see. I'll ask some follow-up questions on that. What can speed up or slow down the half-life process? And that answer was nothing. There's nothing that can speed that up or slow it down. It doesn't matter the temperature, it doesn't matter the pressure. If something's going to decay, it's going to decay, and nothing can change that. I asked something I just said a minute ago, how long a half-life could be. It could be anywhere from fractions of a second to billions of years. Depends on what you're measuring, and they described in the book some really short ones and some really long ones. I asked something else that I just referenced a minute ago. Do these radioactive substances disappear? And that answer is no. Why or why not is a follow-up question there, and the why not is because they turn into other things. It's not gone like vaporized, it's just turned into something else. Number 2 stays the same. The idea of Geiger counters, they explained in the book. Basically, if you have radioactive particles, it lets the gas inside the Geiger counter carry a charge. And when there's a charge being carried to conduct electricity and make a connection, there's a clicker that clicks. Click, 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 click. You know, you get that click, 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 click. You've got a lot of radiation and you need to get out of there. But Geiger counters is staying the same. Curie, it sort of stays the same, but I build off of that. So I'll ask, what's the older unit for radioactivity? And it's the Curie. I'll ask you to define it. The definition is 3.7 times 10 to the 10th disintegrations per second. 3.7 times 10 to the 10th disintegrations per second. So if you have 1 Curie of radioactivity, you have a lot of stuff going on. Because 3.7 times 10 to the 10th, that's 37 billion. You have 37 billion things happening to create 1 Curie worth of radioactivity. And I also asked for the abbreviation. The abbreviation there is a big C and a little I. 4's question is still that way. The newer unit is the Becquerel. I'll ask for a definition there. It's 1 disintegration per second. So if you have 1 becquerel of radioactivity, you have almost nothing. You have 1 radioactive little thing happening each second, whereas in Curie, there's 37 billion things per second being radioactive. Abbreviation for a becquerel is a big B and a little q. Seeing if there's anything else on here that's noteworthy. Mount St. Helens was a famous thing that happened during my lifetime, but well before yours. It was a volcano that erupted. Mount St. Helens had 3 billion curies worth of radon radioactivity. So 3 million curies of radon radioactivity, so that would be 3 million times 37 billion things happening there in a volcano blast. They also mentioned in the book 3 Mile Island is near Harrisburg. It's like a power plant that had a major problem. I think that was in the 70s. There was 2.5 million curies worth of xenon going on there. So that's 2.5 million times 37 billion items happening. There is some mathy stuff in this based on the idea of cutting things in half, so I'll do some math examples now. The main part of the homework is 15 to 20, but there are some other side issues. Basically, if you can cut things in half, you can manage this homework. So I would suggest you make yourself like a little bit of a list of things, 2 columns in a list. So I'm on page 576 looking at example 19.5. Example 19.5 says you have some xenon and it has a half-life of 17 hours. So what I would do is make a column that says start, and then we'll measure it 17 hours later. Then add on another 17. Then add on another 17. And hope that's enough. And if it isn't, I'll add on another 17. Okay, but there will be 1 column that has a start, and then it uses the half-life number you're given, and just count by that number a few times. Then the second column will keep track of the mass. They tell us to start with 0.2500 grams. 0.2500 grams at the first half-life point would cut in half. Just grab your calculator, divide by 2. At the next checkpoint, take this number and divide by 2. At the next checkpoint, take that number and divide by 2. Every time you're counting down 1 half-life worth, you're just going to divide by 2. And there will be something in the sentence here. They say 2 days, 3 hours. So 2 days is 2 times 24, plus 3 is 51. That's where they wanted us to check. So we have that many grams. If we do what we do, which is round the 3rd position, this 5 would round the 2 up to a 3. Next question, similar game. Okay, this time they have strontium. They say half-life is 28 years. So I'm going to have a column with a start. I'm going to have a 28. I'm going to add on another 28. I'm going to add on another 28. If that isn't enough, I'll add on another 28 in a minute. They tell us we're starting with 2.5 grams, and they want us to whittle this down until there's 0.312. So what we're going to do in the gram column, start with 2.5, they told us that, divide by 2, divide by 2 again, divide by 2 again. This is the number they told us that they wanted us to find. So it would take us 84 years to get there. That's the kind of thing you're going to do in the homework. 1 column that goes start, half-life, and counts by the half-life. Another column that has a number, and you divide by 2 to work your way down. I wouldn't rule out that they might give you a number at the bottom ever and make you work your way back up. If they ever did that, if you're dividing your way down, you would have to then multiply your way back up. I wouldn't rule out that they may do that. I'm not saying they are, I'm not saying they aren't. That just occurs to me as I'm thinking about this. They might do that. But we're gonna divide through the half-lives, but if they make you work backward, that also could be doable. Email me if you have any questions when you do the math.